Hello, everybody. I'm back again to continue our discussion on chemical kinetics. Focus is on integrated rate laws. We're going to do the zeroth order case right now. So I would watch the video on first order first. That's I don't want to say the most common, but probably the most common case, with the zero and second order being very common as well. We're going to take a general reaction of just A going to products to give us the overall structure of the formula. And so in that case, the rate, I'll just call the rate R, is just equal to the rate constant. It's not concentration dependent. You can think of it as being its zeroth order in the concentration, meaning it shows up as just a 1 in the equation. It's just having rate equals K. The way this looks mathematically is that's equal to the change in concentration at A, the minus sign because we're focusing on the reactants. You could do this from a product perspective as well, but I will not. This is an easier way to learn it. If you know calculus, and again, if you don't, that's fine, you could think of this as a derivative and solve this by separation of variables and integration directly. And what you would get for your result is that A, and again, I'm going to use the little subscript t here to denote it's a function of time. That's sort of arbitrary, is equal to the initial concentration. I'll denote that with a little 0 minus the rate constant K times T. That's a nice form that you can know. If you don't want to memorize it, you can write it down. I usually give those type of equations on the formula sheet. Let's think about the half-life, and I'm going to have an important statement about this I'm going to make in a minute. So to figure out the half-life, that's when, let's say you have 1 molar of A and you go to 0.5, that would be a half-life, a halving of the material. So we could say that would be 1/2 A naught is equal to A sub 0 or A sub naught minus K, and then I'll just put T 1/2 to denote half-life. When you solve this out, verify for yourself, this T 1/2 is equal to A naught over 2, and we have a K in the denominator. Now, this is not the same as for the first order. The first order was, let's see here, it was T 1/2 is equal to ln of 2 over K. That's quite different. This has concentration dependence in the zeroth order case. In the first order case, it does not. Each half-life time between going from 1 to 1/2 to 1/2 to a quarter and so forth, those time spacings are equal. With these, it's going to have concentration dependency. The half-life between successive halvings is going to actually decrease. And so I'm going to show you what the, this is very wide utility. I would argue this equation has to be used with more caution if you want to use it at all. Also, I would like to talk briefly about the units. If rate has units in, for example, in molarity per second, it could be molarity per minute, molarity per hour, or other concentration units per unit time. This has to have the same units. So it's molarity per second. So whatever the units of the rate constant are, it will be amount of stuff per unit time. That's what the rate constant will have identical units. So that tends to be something people mess up as well. So let's work a problem with multiple stages. I think this works nicely where I do some derivations, but then really focus on working some clear representative problems, and you can blow up the board, lock in and look at it. I'm going to take an equation, a process that's like this. It's known to be zeroth order, and K is going to be given to us. It's 0.100 molar per second. So if you see this, as soon as you see molarity in the numerator and seconds in the denominator, that's units similar to what a rate could be for a reaction. That should say it's zero order, whether I say so or not. So I commonly do that on exams, as I do not necessarily say that. So let's say for this reaction system, we have an initial concentration of species A is equal to 0.500 molar. That could be stated in words in the problem. It could be a particular chemical species. So if I say to you how long to go from 0.500 molar to 0.250 molar, well, that's clearly a half-life. So that time, so the time 1/2 is going to be equal to 0.500 molar, the initial concentration, divided by 2 times 0.100, that's the rate constant, molarity per second, provided I did the math right, check it out, 2.50 seconds. Now, if we asked here the question to go from 0.500 molar to 0.125, that's a quartering. So we go to a half to another half in concentration. You cannot do what you did before and just take 2.50 and multiply it by 2. So if we've gone from 0.500 to 0.250, all we need is one more step to go to 0.125 molar. So what we can do in that case is two ways of doing this. I would argue this way I would not prefer this way. If I was doing it, I would do it as I'll show you next, but I do want to give you two ways of doing it. The second step, we'll call this T1/2, and then this would be T1/2 prime, just to give it a name, is going to be equal to, here's the key point, I'll put a little asterisk here. It is not starting with the initial concentration over here. Now you're at 0.250 molar, divide by 2, the same rate constant, and I get for that 1.25 seconds. So the first step here was 2.50 seconds, and the second step here is 1.25 seconds. It went down, it shrunk. And so the total time to go from 0.5 to 1.125 is going to be these two numbers added together. So that's equal to 3.75 seconds. It is not 2.5 times 2 or 5. So that's an important point, and a lot of people tend to get that wrong on exams, and it's actually really simple. Here's an easier way to work the second part of the problem. So in my opinion, and this would be particularly if you were doing many successive halvings, let's say you were going from 1 unit to 1/16 of it, you wouldn't want to have to do this over and over. Here's a succinct way of going for if you have something where if you're going, and you can use this for any type of process, any kind of decrease. It doesn't have to be something where it represents a halving. So let's say we wanted to calculate this directly without doing those two steps. What I would simply do is use the rate law itself. You can always use that. Let's solve for time. Show this yourself. You know you made a mistake if you get a negative number when you're all done. And let's just plug in values. That's an M. Divided by what was K, 0.100 molar and per second, excuse me. And so what do we get from that? We get, do the math out, 3.75 seconds. If I didn't, I made a mistake on one of the steps, but verify for yourself, doing it both ways. Think about which way you like better. Think about which way works better for you. So that's good. Another thing you can do is with this type of equation, let's just say, so you can always use the integrated rate law. Drop the pen here. So we have the rate constant, we have the initial concentration. Let's say we ask the question for this system, what's the concentration of A after 1 second of reaction? I'll put it 1.00. So we start and we let it go for 1 second. So this is very simply just use this form. And you can just put in, we're starting at 0.500 molar minus K, 0.100 molarity per second, times 1 second. Seconds cancel, it's molarity, it's 0.5 minus 0.1, that's 0.400 molar. So those are the type of calculations you can do with 0th order. Another thing that you should be very aware of, and it's clear from the form of the equations, how the graph looks. This is an equation of the line. Here's y, here's the intercept b, and here's mx. So in this case, if you plot a, or a sub t, however you want to denote it, t, it's going to decrease. The slope is going to be minus k. The slope always has to be, the slope here is going to be negative, but k has to be positive. So if your slope here was negative 1, let's say the slope m is negative 1 mole per second in an arbitrary example, then k would be 1 molarity per second, right? So you would have, it's always going to be positive. The intercept is going to be a naught. I'm going to put an asterisk here because the people on the exam, when I put this question on there, there'll be a question where you sometimes have to identify order. Sometimes we'll say, you know, maybe what order is it? Or sometimes I actually have to do a calculation based from data from the graph. Like I give you a equation of a line generated by that, so you're able to pull out what the rate constant is, and I have to figure out the units. If this is in units of molarity and this is in units of time, in seconds, then rise over run has to give you molarity per second when you have a line plotted like this. A lot of people go to the first order. I do not know why. Probably because they see A here and it looks like it's raised to the first power. That's not what this represents. This is representing a 0th order reaction where rate is equal to K, but we're plotting the decrease in concentration over time. The concentration will decrease over time, but it's decreasing linearly as a function of the concentration, not the log. The log, the natural log, and you could do it with log base 10 if you care to, but we're going to use the natural log. The logarithmic decay that looks like this, if this was ln of k, ln of a decreasing like this versus time, that's a first order. But people tend to go for a gut feeling of like, oh, it's a to the first power, it's first order. That's a misunderstanding of the material. So focus on that, understand what this plot looks like versus the natural log plot that has a similar shape but a different axis. If you plotted something like this, for emphasis, ln of a sub t versus t, and you see this, that's a classic first order case. This is a 0th order. So on that note, I'm out. I hope everybody has a great day. Depending on the upload time, that's my limiting factor. I'm working from Long Island, New York. The uploads take sometimes an hour, sometimes they take 3, 4, 5 hours for these videos. Depends on whether I'll get another video up today. A few people are watching. Well, we got over a month before the semester. But for those of you watching, I hope you enjoy. If you have any comments, you can put a comment in the box. If it's a comment about my grading policies or something like that, don't ask that there. You can email me. But if it's a question about the video, you can ask me in an email or you can put it in the comment box, and I'll try to answer it to my best of my ability. On that note, I'll maybe make another video today, maybe not. So have a good day. Take care.